Welcome to the AI Research Roundup. I'm Alex. Today we're looking at a paper trending on X, published on February 26, 2026, which was just about 4 days ago. It introduces a new optimization strategy called LITE that achieves a remarkable 2x speedup in training large language models by specifically targeting the flat directions in the loss landscape where progress is typically slow. The paper is titled Accelerating LLM Pre-Training Through Flat Direction Dynamics Enhancement. And as we'll see later, the efficiency gains hold up across different architectures and scales, which is really impressive. And for those interested in the implementation, the authors have shared their code on GitHub. So, Figure 1 visualizes this performance gap explicitly. On the left, we see training curves for a 0.25 billion parameter llama model trained on the Pile dataset. The cyan lines, representing muon LITE, drop much faster than the standard muon baseline shown in black. In fact, that red arrow highlights a clear 2x speedup, meaning it reaches the target loss in half the iterations. Then on the right, the scaling laws plot confirms this holds as models grow, because muon LITE consistently achieves lower terminal validation loss across all parameter counts. Alright, Figure 1 showed the results, and now Figure 2 explains the underlying geometry that makes them possible. The histogram on the left reveals that the landscape is dominated by flat directions with near zero eigenvalues, while sharp directions are actually quite rare. The schematic on the right translates this into a narrow valley structure. You can see standard optimization, in blue, wasting time oscillating between the sharp walls. In contrast, the red line shows how the LITE method drives progress along the flat valley floor, effectively speeding up convergence. Okay, while Figure 2 illustrated the landscape, Table 1 details the actual update rules for the optimizers operating on it. It compares n-atom-w, muon, and SOAP side by side. The crucial distinction lies in the last column, labeled F, which represents the curvature metric each method approximates. Notice that n-atom-w relies on a simple diagonal term, effectively treating each parameter in isolation. In contrast, the muon and SOAP rows show much more complex matrix forms involving Kronecker products, which allow them to capture the correlations between parameters that diagonal methods ignore. So, Table 1 laid out the baselines, and now Algorithm 1 shows how LITE modifies them to speed things up. The process starts at line 4, where the method estimates a projection matrix, QK, to explicitly identify the flat directions in the landscape. The key innovation appears in the highlighted equation at step 5. Here, the update is split. The flat component is multiplied by an acceleration factor, chi, and uses a stronger damping term, beta 2. This lets the model move aggressively along safe valleys, while remaining cautious in sharp directions. Well, Algorithm 1 relies on identifying sharp directions, but calculating the full Hessian to find them is too expensive. Figure 3 validates a crucial shortcut. The charts compared the true Hessian's top eigenspaces against those estimated from gradient statistics. On the left, the green bars show that for row Hessians, the overlap is nearly perfect. The orange bars on the right show similarly strong alignment for columns. This confirms that the optimizer can reliably estimate the landscape geometry using just the gradients it already computes. Alright, Figure 3 confirmed the method works in theory, and now Figure 4 demonstrates the actual performance gains across a range of llama models. The 4 panels track validation loss during pre-training for model sizes ranging from 0.13 billion up to 1.3 billion parameters. In every case, the solid cyan line representing muon LITE drops significantly lower than the black dashed baseline. The intermediate orange and pink curves show that while individual components help, combining them consistently yields the best results. Okay, while Figure 4 focused on pre-training loss, Table 4 reveals how well that translates to actual zero-shot performance. It compares the 1.3 billion parameter model trained with standard muon against the version trained with muon LITE. The results are consistent across the board, with muon LITE achieving the highest score in every single category. Notably, we see a massive jump in bool Q, rising from roughly 52 to 60.5%. Reasoning-heavy benchmarks also see solid gains, with ARC challenge up by nearly 2 points and MMLU showing clear improvement. Wrapping up, 2 takeaways stand out. First, by explicitly targeting flat directions in the loss landscape, the LITE strategy allows optimizers to accelerate safely where progress is usually slow. Second, the consistent 2x speedup implies we can train powerful large language models with significantly less compute. It is a major win for efficiency. That's it for this episode of the AI Research Roundup. I'm Alex. Thanks for listening.